is it? Say it again. Sorry. What?
Length.
No, what's the property number?
3.52.
Thank you. All right, go ahead. You got a wire. Let me just sketch this out. You got a wire, and the length is what?
5 centimeters.
5 centimeters. Got it.
Diameter is 0.812 millimeters.
All right, so now we have a diameter D equals 0.812 millimeters. Is that right? Okay, what are they asking for?
Determine the resistance and the power dissipated when 10 milliamps.
Okay, so they're saying that they've got this resistance, I'm assuming it's copper, right?
Yes.
All right, so that's 5.8 times 10 to the 7th Siemens per meter. And this is really just a classic resistance problem. It's a very easy problem. And you have, how much current again?
10 milliamps.
I equals 10 milliamps. Okay. Is that thing working or not? Still working on? Hey, look, if you got another, anybody else have a paper clip or clamp or anything I can use? Because that thing.
I fixed it, it's just I can't get the audio to come through.
If you open it up, there's an on switch there, and then there's an on switch on the top. Just keep tapping, it'll work. Anyway, or check up here, make sure the audio is on.
Tap it harder.
Are y'all with me on this one? Now first, you have to make sure you understand how to do the resistance. This is a trivial problem. It's constant cross-section. That was the first one I did. How many remember that? If we wanted to go through the proof on it, you asked us, this is a very straightforward problem. Generally speaking, you assume I, right? Then you get J. Now I'm going through this one time. You do it a few times, you'll know this by heart, all right? The next thing you're going to get is J. And J is simply equal to I over the cross-sectional area in the direction that's flowing. I'm going to just call this the Z direction. Doesn't matter what I call it. Y'all with me, class? So now we need the area. What's the area? What's the cross-sectional area of a wire of a certain diameter? Well, it would be what? It's pi a squared if a was the radius, right? Or pi d over 2 squared if you're going to use diameter. So this is pi times diameter over 2 squared. Really what it is pi times d squared, right? Over 4. Can you tell me what that is? I'm just putting them up here so everybody has this. This should be in the solutions, by the way. I think. I don't know for a fact, I haven't looked, but can you tell me, anybody? I always feel a little foolish asking this, but if you have your calculators, I ask this all the time. Get them out, just make sure you got no problems. This is a trivial calculation. D is 0.812 times 10 to the minus third. Do you agree with that? Square that, multiply by 5 pi, and divide by 4. I can't tell you that off the top of my head. Anybody? Anybody at all? How many engineers does it take to fix a clamp? You'll never know. Go ahead. What was it? Nobody? Anybody?
0.164 pi.
0.1645? Is that right?
Pi.
Pi.
Yes.
No, I want it in terms, just a number.
0.5178.
Hold on. It's gotta be, that's millimeters. That's gotta be 10 to the minus 6 or something. Say it again. 0.1?
So this would be 5.178. So
Five
times
point-
10 to the negative 4.
10 to the minus 4, that would be meters squared, right? Remember, I like meters, I don't like centimeters squared. I like always MKS. You all with me, class? All right, next, after that, I've got I mean, I'm gonna just leave it in general terms, all right? Don't worry about VI. Leave it general, right? So we've got this, and this really is gonna be, and I'm gonna put it in the general term. We'll use this in a second. So this is gonna be I right there over pi, and here it's d over 2 squared. And so that's going to be the actual current density AZ. What's my next step? You remember? That's current density. After I have that, what do I get? That's J. Remember this always. J is equal to sigma E, right? And we know the integral of E dot dl over the length of the wire is the voltage. We're going after the voltage. If we have the voltage in terms of the current, then we have the resistance. Do y'all follow? The logic is clear. So we've got this. I'm not even going to be bothered putting in the value for D here. I just want that calculation. All right? Now after that, what do I do? Now I get E, right? And I say that E is simply equal to J divided by what? Sigma. Y'all see it over there? Now you have the E field. That would be volts per meter. I can write it down for you. That would be I over pi d over 2 squared times sigma. It would be in the AZ direction. Finally, I'm going to get the voltage. One thing you notice about the E field, it is not varying spatially. It is a constant value. This is your best friend. If it's a constant value, just multiply it by the length over which it's, you might say, or the length over which you want the voltage. So it's the E field is in the Z direction. We could integrate E, right? E would be in the AZ direction, and DL would be DZAZ. Do you all follow me on this? The only thing you're going to do is take that E field and multiply by the length. How many remember me doing this type of problem? Anybody? I hope you all do. Good. So really, now I can get the voltage V across that is really, technically it's the integral of E dot dl over the length, but we can see because it's a constant E field, we get I over pi, and it's D over 2 squared sigma, and then it's just going to be times the length, L. And that would be the voltage. Does everybody see this? Let me see your hands if you do. I want to make sure I'm not doing something where I'm assuming you see it and you don't. Y'all see it? All right, finally, the resistance. Always think Ohm's law. V equals I times R. Therefore, if we divide V by I, we get R. And the resistance is simply equal to, it's always proportional to L, it's inversely proportional to sigma, and it's inversely proportional to the cross-sectional area. So that's pi d over 2 squared, right? And that's going to be the resistance. Now, we've got area here. That's what this is. This is the area. I'm not going to throw that. We've got, this is the area, right? No? Mark is really put this all. Y'all with me? That's the area. Y'all see that? All right, go ahead and do that. The length is what? 5 centimeters. That's 5 times 10 to the minus 2. So what is the resistance? You can plug it in. Sigma is 5.8 times 10 to the 7th, right? Y'all with me, class? I'll give you the conductivity for copper, aluminum, whatever you need, but in general, it's something you're probably going to need to know because it's so common. So what is this value?
I got 1.66 milliohms.
1.66 milliohms. Anybody confirm or deny that? Okay. You clear on this? Now, this is a straightforward problem. In general, what I always tell people is, if you have a resistance and the cross-section is constant, doesn't matter what the cross-section is. If the area of this resistance is A, and then you want to know the resistance over any length, doesn't matter what that is, and you want to know the equivalent resistance of this thing, that R is always proportional to the length, whatever the length of this is, always inversely proportional to the cross-sectional area. This should make perfect sense. If you think about what happens with resistors in parallel, if they're the same value, divide by the number of resistors in parallel to find the parallel resistance. Do y'all remember that? Well, as the area gets big, what you're really doing is making more and more, you might say, resistors in parallel. You can think that way about it. That's not exactly. Do y'all follow me? There's more area for the current to flow through. So it's inversely proportional to the area, and it's inversely proportional to conductivity. And that's it for constant cross-section, if the conductivity doesn't vary spatially. Now, if it does, it's a little more complicated, but that's it. Y'all with me? Show of hands, how many see this? Now, you want the power. Think back to the days when you did circuits. Final exam kind of question. You got R, and you got a current, I. Assume it's a DC current. How much power is dissipated by that resistance? Anyone?
PR. I swear.
You could say I can find the voltage, it's R times I, and I can multiply the current. So it's R times I, or RI squared if it's DC. How many understand? So that's it. Watts. So for this, what is it? You take 1.16 times 10 to the minus third times 10 to the minus 2, so it's 1.66 times 10 to the minus 5, or 16 microwatts of power, roughly. Y'all see that? How many do? It's really, there's nothing tricky about that, I'm being honest with you. It's a straightforward problem, just do it methodically in your mind. Make sure you see this. You got another one for me? I don't know if that was the first one I gave you or what, but usually Whitworth has things where he has wires and you'll have an inner core that's different than the outer core. Do y'all hear me on this? So what you have to do is find the resistance of the inner core wire and put that in parallel with the resistance of the outer core, where you have, now you have something between, like, you might say A and B with a different conductivity. Do y'all follow me on this? How many understand at least the rationale? Y'all, you guys good on that? All right, but the ones that usually are more tricky, where you have a variable conductivity versus position in spherical or cylindrical coordinates. Did you have another question or not?
I was gonna ask, if I was gonna try to set up the integral on that,
Yeah.
what would my balance be?
Just from 0 to L. It's over the length. That's all it is. How many see this right here? There's nothing tricky about this at all. All right, and it's always positive, because the resistance will always be positive. You don't have to worry about getting the sign wrong, if you think that. Yes?
Is that W watts or is that?
Right here?
Yeah, kind of.
That has to be watts. Power is always in watts. Y'all with me? All right. You got another one? I got one for you. Yeah.
I don't have that in front of me, but somebody do the last one, it was 3.56.
Yeah,
Sure
sure.
that was.
Yeah, I'll do it. I like doing, honestly, discussing problems, whether you did them or not. Discussing them, and if you force yourself to think, how would you solve it? Find the place where you don't know the next step, and then let me answer it as best I can. So it's a real way to learn. I remember, now this is a long time ago, we had blackboards and chalk and stuff, but myself and a few of my friends, we would be working physics problems, and we'd go through and try to do every single physics problem. And we put them on the board, and a lot of times what happens is you get stuck, and then everybody's looking and somebody figures it out. They figure out what step you're missing. And that's really helpful. Okay, next part, this is 5/6, did you say? All right, so give me the specifics, please.
It says a nickel wire of diameter 5 millimeters is surrounded by an
Okay.
4.5 millimeter cable.
This is a classic problem. Yeah, this is a Whitworth problem. So this wire is nickel, all right? I'm gonna say it's got an inner radius of A, and it's got a big one per meter or not?
Per
It
unit.
has the resistance per unit.
Okay, so length is just one, all right. So I've got a radius A, I'll get to that radius in a second, all right? This is nickel. It's got a conductivity associated with nickel, all right? I don't know what it is, but just with me on this, class? Now, it's surrounded by another sheath. This is in a radius B. So we've got The second one, is that copper or what? Silver? Silver's got a great conductivity. So this is the sigma of silver for an AG. And now, I don't care what the values are right now. I'll put them at the end. Now, take a look at this. Can you see what this problem looks like? Because remember, when you're talking about resistance, you're really talking about something where when we put a plus minus voltage across there, the same voltage is going to be across the inner core as the outer sheet. Do y'all follow me on this? Let me see your hands. Y'all follow me? Same voltage, so they're in parallel. Same voltage across any two resistors, they got to be in parallel. If you remember when you took circuits, right? When you trace those diagrams, if the same current goes through any two resistors, they're in series. Same voltage across, they're in parallel. It doesn't matter how the drawing works. Do y'all with me? So now, come over here, and it looks like this. You got a resistor here, and I'll just call it R nickel, and it's in parallel with the resistor here. And I'll call it R silver. All right? So this is per meter. So R nickel is again L over sigma A. I'm just putting the general form. Constant cross section, y'all follow me? Two wires, the cross section doesn't vary. You with me, class? So over here, since it's per meter, you can just say L equal 1. This is going to be 1 over sigma of nickel times the area, which is going to be pi a squared, right? And we put the radius down of the nickel wire. Do y'all agree with that, class? Now, what's the actual resistance of the silver one? Well, just look at this. Now we're talking about this is the cross-sectional area. Y'all following? It's between A and B. So if I look straight down, you might say the z-axis. What I want to know is this. I want to know how much area is in here. That's radius A. That's radius B. The method I'm going to use is, I'm not going to do an integration. I'm going to take the area as if the radius of the wire was B. So it would be pi B squared. Now that's the total area of a radius B. You all see that? And I'm going to subtract that inner area from it to get the remainder, which is the sheath area. So now I subtract pi A squared, and that's my area for the cylinder. So now I come over here, use the same method. The length is 1, so it's 1 over sigma A, and that's 1 over, and I'll just put it sigma silver. This is the highest conductivity material in the non-exotic materials you can find, by the way. But it does oxidize. That's the one bad thing about silver. Gold is usually used if you don't want oxidation, you have to have a high conductivity. And then it's going to be pi, and it's going to be B squared minus A squared. Y'all agree? Now, what do we do to get the total resistance? They're in parallel. Do y'all agree? If they're in parallel, what would the resistance be? It would be 1 over R, I can call it nickel, plus 1 over R silver, AG. Do you all agree with that? I'm going to say this right. It's not hard. You can multiply them if you want. R1 times R2 over R1 plus 1. Doesn't matter how you get this. They're in parallel. Correct, class? So go ahead and do this. What is R of the nickel? Just first, I guess I need the actual conductivity of the nickel. That I don't know. Anybody?
6.2
So 7.2 what?
6.2 e to the 7.
That's silver. That's silver.
1.5.
All right. Hold on. All right. So it's 1.5 times what?
10 to the 7.
10 to the 7. And then for silver, it's 6 point what?
2.
Times 10 to the 7th, right? You got those two values? What is A, the inner radius A?
Inner radius will be the 5,
What?
or will be 2.5 millimeters.
2.5 millimeters, and B,
3 millimeters.
3 millimeters. Okay, you can do this as quick as I can, obviously, I'm asking you to do it anyway. But now it's just plug and chug, right? So if you get this, what is this resistance in nickel be, just for completeness? You probably asked. What is it?
3.4 times, or millimeters, or 3.4 times 10 to the negative 3.
Milliohms, right?
Milliohm, yeah.
Milliohms, and what is it for AG?
But it's over, M, ask for per length.
Yeah, this is per meter. I put L equal 1. All right, so what is it for silver? For the outer part of the sheet?
1.87 milliohms.
Okay. 1.87 milliohms. Can everybody take those in parallel? What is a parallel combination? You can multiply them and divide by the sum, or you can take 1 over the first plus 1 over the second. Did you have a question, sir? Yeah, go ahead, ask.
I'm just stretching.
No, him.
I was just trying to figure out how you got A and B.
I got what?
Those already.
Those are the radiuses given in the book. He takes diameter by 2 if it's diameter.
Okay, I might be looking at the wrong problem.
No, yeah, you told me ones is.
What's that? You got it?
5 divided by 2.
You got to divide by 2 if it's diameter. Are you good with that?
Yes.
Everybody good with it? That's the way you do it. What would happen? I haven't done this one ever. This is an interesting thought. What if I put another sheet on? Make that gold.
Still in parallel.
That's right. How dare you? It's a logical extension, right? Now you get the area between B and C, right? Use that and you find the conductivity of gold, and it's just 1 over the conductivity of gold times pi quantity C squared minus B squared, and then you got 3 in parallel. I'll give you a tip. If you get anything more than about 3, don't use R1 times R finding one combination and parallel again. Just do 1 over the first resistance plus 1 over the second plus 1 over the third plus 1, because you go nuts doing this when you get about 5 or 6. Y'all follow me? It'd be easier that way. All right. Do you have any more questions? Because I'm going to do one quick one with you, then we're going to do capacitance. All right. Those problems, by the way, I think in physics you do a fair number of these types of problems. I'm not certain you do everything. We'll do one problem, and we'll talk about power density and things like that. And first, we do capacitance. After I do this one problem. Now, remember, I really like cylindrical and spherical symmetries with conductivity or permittivity that vary spatially. Write it down, it's coming at you. Y'all hear me on that? So, here's a classic problem. I'm going to have a spherical resistor of radius A, an outer radius B. This is a spherical resistor. You could drill a little hole if you want. I do this only to help people get a good metal understanding, and then ground the outer layer right here. And I'm going to put a conductivity, but this conductivity inside here is going to be some sigma 0 times R, and the units would be Siemens per meter. Y'all follow me on that? So basically, I have a conductivity. I didn't specify sigma naught, but it's sigma naught times R. So the further out it goes, the larger the conductivity. Can y'all follow me? And again, R is measured from the center, so this would be R. So I want the resistance between the inner and outer conductor. Now, think with me about this. You've got to assume something. If given a choice, assume current. I assume the current. What's my next step? That's right. And the actual thought process is this. The integral of J over the surface, closed surface, is the current flowing through a surface. It's identical to Gauss's law. Remember the integral of d dot ds was the charge enclosed? Well, here, the integral of j dot ds is the current enclosed. Now, if you look at this, if we have a spherical surface of radius r, all the current flowing from the inner surface to the outer surface has to pass through that surface. Does that make sense? So we can say that from I can get j, and that's simply equal to I over 4 pi r squared, and call it in the AR direction. Now, does everybody understand it? The surface area of the sphere is 4 pi r squared. Good with that? What's my next step, anyone? No wrong answers. What? There's no wrong answer. Think about it. We got J. Let me think. Oh, it's erased. E, right? Divide this by sigma. Correct, class? All right, so now we get E. And that's going to be J over sigma. So that's I over 4 pi r squared. This is the way I like to see this on any kind of a quiz or test. I can understand the rationale you're using. When I just see this, that, I don't know what you're doing. But I have to see the logic to give you any kind of real credit. Y'all follow me, class? Now, I divide that by sigma. What is sigma? Well, I made it up, but it could be any function of r. So this is sigma naught, right? R times r. Where I can make this r cubed. Now, can y'all follow me? On purpose, right? Sigma naught times r is sigma. When I divide that, I get an r cubed times sigma naught. Y'all follow? Now I need the voltage between the inner and outer conductor, right? So I can say that voltage, you might say VA, if you want to do it this way, minus VB, we know it's going to be strict positive at the end. We're after resistance, is equal to minus the integral, and this is going to be from B to A of that, this whole thing. So it's actually, I did it wrong. What I'm going to do is just put it this way. That way you won't get confused. From A to B of the E field, which is this, and that's I over 4 pi sigma naught. Now it's r cubed AR dot. Now normally DL would have dr AR, and then it would have r d theta a theta plus r sine theta, and it would be d phi a phi. Now I'd give you that on the exam, but because the AR, this only has an AR component, when you do the dot product, only the AR term will survive. Y'all follow me? So I don't rewrite that all the time. So this is going to be AR dr. Now, when you do this, what happens? I can take the constants out in front and I get I over 4 pi sigma naught. What is the integral of 1 over r cubed? By the way, this one stings people oftentimes. Well, it would be what? That's r to the minus 3, correct, class? So normally you'd have 1 over 1 minus 3, or 1 over minus 2, or minus 1/2. Do you all follow me on this, class? So it'd be, there's a minus on there. It would be minus 1/2, and then it would be r to the minus 2, or 1 over r squared. Do you agree with that? Everybody? When you do it, what do you get? You get, and actually this would go, and this would go, and it would be 1 over A minus 1 over B, and that would be the voltage difference between the inner and outer conductor. Do y'all follow me, class? Show of hands if you do. I'm just doing the integral. What's the resistance finally? Divide by I. All right, I've given that very problem that I put up there on a quiz or a test some time ago, and I was shocked at how many people messed up the 1 over r cubed integration. So I'm giving you a hint. An odd integration is not just 1 over r squared could appear, but it would be 1 over r to the n kind of deal. Y'all with me? Yeah.
Why do we assume some current I and carry that through?
How would we get resistance if we didn't assume a current?
We know,
We need the ratio of I to, or V to I, right? So you could assume V and get E, from E get J, from J get I. But you have to have V and I to calculate resistance. That's the reason we assume I.
well, we do know that it's proportional to the length and area of the place.
Hold it, there's no length theory, right? This is a spherical system, not a planar system. I mean, there's a surface area that's ever increasing. It's not constant cross-section. So here you have to start by assuming I. Does everybody follow me on this one? If you don't assume I, you can't do anything, because what you're really after is a ratio of voltage to current, right? I mean, how are you thinking about it?
So integrate from AC
Of what? What are we going to integrate?
of, DR is.
Of what?
DR,
DR, differential resistance or differential length?
a radius,
Differential radius, okay. What are we going to integrate?
and then it's times,
What are you integrating? That's DR as a differential. What function in front of it?
you have 1/sigma times 4 pi r squared, which is.
That's E, right? Isn't that right?
Yes.
We got E from what? From J. We got J from I. You have to start with the assumption of either V or I. Typically I for cylinders and spheres. From I, you need to get J. From J, you get E. And from E, you do the integration, get V, and then you take V by I to get R. You can't do it any other way. I mean, if you assume V, then you have to solve Poisson's equation to get the form of E. And that's something, you're asking for more work than it's worth. It's much easier this 11, okay? All right, now, yeah.
Is A supposed to be squared, A and B, so there?
Oh, gosh, my gosh, so sorry. Absolutely. It has to be split. That's on me. Thank you very much. I'm ready. All right, I want to do some stuff. Now we're going to move to capacitance. It's the same technique that I've showed you here. Only now we're going to assume charge, calculate D, calculate E, calculate V, and capacitance is charge over voltage. Now, you've done these problems in physics, but I'm going to take you through it. Just remember the methodical steps. I'm sorry. So, and I'm going to start, since I just did this one, I gave a problem where I've done this a couple different times, where I had either a cylinder with both a conductivity and a permittivity that varied spatially, and I asked you to calculate the resistance and capacitance between the inner and outer radius per meter. And I've also done a sphere with a variable conductivity and a variable permittivity, and asked for resistance and capacitance. So I'm going to do it, I'm trying to show you the similarities. I think you did it though. All right, so for this one, this is capacitance. All right, for capacitance, the symbol is obvious, right? Capacitance is really something that's proportional to the amount of energy you can store if a given voltage is across the difference in the plates. That's it. I don't want to get too deep into different philosophies about how you explain capacitance. It's that simple. You're electrical engineers, you have capacitance. So this is an energy storage device. So if we're going to do capacitance for any type of a structure, we're going to go the same method. We have to assume something. So we assume Q or V. I'm going to assume Q. After I get Q, that would be a total charge on a plate. I'll show you how it's applied. Does everybody follow this? Now, you're going to get the D. And you get it by taking Q over the integral of the surface, really over ds. And I'll explain that, but we get D. After we get D, we get E. And E is D over epsilon. Now, epsilon can be a function of position. I'll talk a little bit about epsilon relative in a second. Y'all follow me in this class? After we get E, we get V is equal to the integral of E dot dl. I'm doing this in a general way. I know capacitance is going to be strict positive. That's the reason I'm casual about the sign right there, okay? Let's apply this technique to the same system we just looked at, a spherical system. So if we have this, inner radius A, outer radius B, this is spherical now. And here we're going to assume we have epsilon, it's going to be a function of position. Let me go ahead and do this for you. I'm going to assume epsilon is, say, epsilon naught over R. That would be farads per meter. So it's times epsilon naught, and it's divided by R. Now, I haven't really talked about this, I don't think. But you know, in materials, you've seen epsilon is equal to epsilon relative to epsilon naught, right? And epsilon naught, how many know what epsilon naught is? Either form. Anyway. How many do? Go ahead. Whoever says. What?
No, just whenever.
Anybody? Yeah.
8.854.
8.854 times 10 to the minus 12, right? Times 10 to the minus 12 farads per meter. The other formula Whitworth likes a lot because the pi's cancel on equations is 1 over 36 pi times 10 to the minus 9 farads per meter. They're almost the same, not quite. Remember how the speed of light we approximate is 3 times 10 to the 8th meters per second. How many know that? The real speed of light is 2.999 with a lot of other stuff after that. It's almost 3. These are approximations of the actual value of epsilon. They're not exact, just remember that. Okay, so let's do this problem. Inner radius A, outer radius B, the permittivity is given. By the way, epsilon relative is something that varies from about 1 to fairly large numbers if it's exotic, but 1 to about maybe 5 or 6 for most materials that are common. 2.2, 3 is typical, 4 for some very good energy holding materials, but epsilon relative just gives you an idea of how much better that material is at storing energy in free space. Now that's the way I explain it. There are probably other theories, but that's really it. And epsilon relative, the reason these things store energy and stuff like this is because, frankly, the dielectric in them stretches like little springs. You have positive and minus, you put an E field, you stretch that, and they store energy in these little spring-type systems where they have any kind of a dipole moment. Y'all with me? And that's it in a nutshell. Okay, so now we're going to assume Q. I'm going to put a charge Q at the center here. So I assume Q. Now I get the D field. Remember what I told you, this is spherical. The D field at any given distance between the inner and outer conductor at a radius A, well, it's going to be the total charge over 4 pi r squared. It has to be the D field from Gauss's law. How many know that? Y'all with me on that? Remember, the integral of D dot ds is charge enclosed. If it's spherical, it's always 4 pi r squared if you're going to use Gauss's law. So the D field is just Q over 4 pi r squared AR. With me? I'm omitting the units, but it would be what? Coulombs per meter squared. What's the next step?
An E field.
E, right? Now I say that the E field is simply D over epsilon. I made it that. Could be anything, so it's Q over 4 pi r squared, and epsilon here, I made it epsilon naught over r. It could be any functional form of r. It could be epsilon naught times r. It could be epsilon times r to the 3/4 power. Do y'all follow me? It can be any function of r, as long as it's not a function of phi or theta. Then it wouldn't have spherical symmetry. After that, it's in the AR direction, right? How do you go ahead and reduce the complexity? Can you all see this? I have Q over 4 pi r squared, epsilon naught divided by r, right? So just reduce r squared to simply r. Do you all follow me on this, class? Can you guys see it in the far back? better than me. Alright, so I'm just gonna make it R epsilon naught. Next thing I need is the voltage, right? Remember, it's gonna be strict positive. What's the voltage gonna be? Well, the voltage difference, we give it as the integral of E dot dL, right? And you can say between A and B. So that's what? The integral of Q over 4 pi epsilon naught R, AR, dot AR dr. And we go from A to B. I'm not even bothered with the negative sign. Do y'all follow me? How many do right here? What's that gonna be? AR dot AR is 1, and we get a voltage between the inner and outer conductor of simply, it's gotta be proportionally Q over 4 pi epsilon naught. What's the integral of 1 over R, people? Natural log, right? So it's the natural log of the outer radius B over the inner radius A. Finally, what's the capacitance? Let me put it up here. People do make mistakes here. Q is equal to C times V. Well, V is indicating the voltage difference between the plates. Q is the charge on one plate, absolute value, and C would be the capacitance. So if you look at this, C is equal to Q over D. It's inversely proportional. Y'all with me? Now look over here. That means when you take 1 over that, right, and multiply times Q, you get what? 4 pi epsilon naught over the natural log of B over A. Can y'all follow me on that? I warn you, don't just memorize formulas. This is a capacitor for capacitance of a spherical surface or spherical surfaces, cylindrical surfaces, and stuff like this, because it's dependent on epsilon. If epsilon varies in a different way, just take a look at how big a difference would happen. If I made epsilon not R, y'all with me? Well, if I did that, this would be R cubed here. Then if I integrate that, I get minus 1/2 over R squared, right? Evaluated between the two radiuses, and you get a totally different answer. So just remember to go through this methodically. Don't take a shortcut. Oh, I remember that. That's the answer. No, it isn't. Just go through it methodically. You good on that? Finally, the last thing I'm going to do, so this is capacitance. And in his book, how many remember at least having capacitance in physics? Do you remember him going through this stuff, or Bert going through this kind of stuff with you? I could go through it for cylinders, I can go through it for planar structures. The mythology, the method you use is the same. And for some planar structures, you assume V first, because it's easier. But almost always, for any spherical or cylindrical surface, you're going to get capacitance between, or resistance. You start with either current or charge. Just remember that. It'll help. So now, another thing I'm going to talk about. I can spend a lot of time with capacitance, but I think you can, because you just had the actual, we just did stuff with resistance. I think you can handle it, but I'm going to talk about one thing, actually two things that I think people sometimes make mistakes on because they're missing just a small piece of understanding. And I'm going to try to make it clear. And I'll show you, as an engineer, how I think about it. So what would you do if I asked you the capacitance, and I have an inner radius A, outer radius B. This is going to be a little different. Now I'm going to say that I have exactly half of this capacitor filled with some epsilon relative 1, and the other half with epsilon relative 2. And I want to know the effective capacitance between the inner and outer radius. Y'all follow me? Think about it. Now use your rational mind. Couldn't you say that there's a net capacitance on this side? Forget this side. Between, call it C2, capacitance there. Y'all see what I'm doing here? That's between this surface and this surface. They have to be the same equal potential difference from here to here as here to here. And a capacitance between, on that side, where the second or the first epsilon is. How many see this? How would you calculate, if epsilon was constant here, just listen, how would you calculate this capacitance? Could you get the capacitance for an entire sphere filled with epsilon relative to? Yeah, we could go through it. We're out of time just about, but that would be why. If you just had a total spherical surface, let me put it up here so I can reference it. If you have a total spherical surface of inner radius A, outer radius B, with some value epsilon relative, just call it epsilon relative. We could start by assuming a Q, getting D equal to Q over 4 pi r squared, then dividing that D by epsilon relative to epsilon naught, and integrating. At the end of the day, we get the standard formal integral of it would be a 1 over, when we integrate the 1 over r squared business, we're going to get 1 over A minus 1 over B, and it's going to be times charge over 4 pi epsilon naught. Trust me on this one. When you invert, you end up getting the capacitance between the inner surface and the outer surface of that sphere is 4 pi epsilon naught epsilon relative over, and then it's going to be 1 over A minus 1 over B. You're going to have to trust me on this one. You all with me? You can do this. Please do it. All right, now I'm going to make a rational statement. I'm showing you how to think about these. If the whole sphere, if it was filled with epsilon relative 1, had this capacitance, what would half the sphere have? Just half that, wouldn't it? Take this value, divide it by 2. Do y'all follow me?
Yeah.
How many do? How much capacitance would be here? I mean, from this is called this epsilon relative 1. On this side, it's going to be that value right there with epsilon relative 2 divided by 2. How many see that? How many see they're in parallel? Capacitors in parallel add like resistances in series. That's the way I do that kind of a problem. Do y'all understand that? Now, the final thing I'm going to say is this. What if I had a capacitor that looked like this? Inner radius A, I got a radius B, and then I got a radius C. And this is, say it's a sphere, and there's going to be some epsilon relative 1 here, some epsilon relative 2 here. What does that look like to you intuitively? Think about it. If I'm looking for the capacitance between A and call this C, inner and outer radius. How many see? It looks like you have a series capacitor between A and B in series with a capacitor between B and C. How many see that? What are capacitors in series? How do you add them up? That's right. Now, you see, we could go through the mathematics and assume a charge, get the D field, do all the 9 yards on that, but it's a whole lot easier to see through the problem. Just realize that. Y'all follow me, class? I'm trying to give you some glimpses of the way, at things the way I think about it. Go ahead.
Do you not need a capacitance between A and C there?
This is the capacitance between A and C. It's this one plus this one. That's all. I mean, you have to add them. Boy, I hate to do it. 1 over CAB plus 1 over CBC. Y'all follow me, class? I'll see you. We're going to do a quiz on Friday. Next time, I'm going to give you some problems. I'm going to give some reading, and I'm going to finish this. Hopefully, finish this. Maybe finish this chapter next time.
What chapters are gonna be on the test? 1 through 3?
13th is when? That's a couple of weeks, right?
That's next week.
That's next Monday.
Next Monday.
It would be everything we covered through the next lecture. So anything new on Friday won't be on it.
Do you want to do a review session?
Friday.